All right, welcome back. My name is Jesse. I am a tutor in Melbourne. I've been a tutor for around about 12 years now, actually, and I sat the GAMSAT last year, did pretty well in Section 3, decided to start making a bunch of videos on it that have seemed to be pretty helpful to people. So what I'm doing today is the 11th of sample Section 3 kind of walkthrough videos. I basically write my own questions that I think reflect the real exam and the way that it's kind of trending. And it's designed so that they're both practice questions that you can do in your own study, so that you've got a bunch more free questions. It's linked all below on my resources page if you haven't already checked it out. And then this video acts as kind of the worked solutions, and it also shows the way that I would tackle GAMSAT style questions and work through them methodically. People have requested to see a little bit more on logs and acids and bases and fractions and that kind of thing. So I thought, let's bundle that into this particular video today. We've got 7 more questions. I think there's now over 100 practice questions that I've put up on the resources page. So I think that's pretty cool. And I'm going to basically just keep doing them. There's going to be more people needing to sit the GAMSAT. So I think 100 questions is good. 200 is even better. More than that is even better as well. So if I can keep kind of banging these out every now and then we can slowly amass a bigger and bigger amount of free resources for people to use so that people don't have to fork out money for crazy overpriced courses. So basically, we're going to go through, pun intended, I guess, with acids and bases. We're going to go through this unit here that I've put together. We've got hypochlorous acid, HOCl, is a common ingredient in pool cleaner due to its antimicrobial properties. The dissociation of hypochlorous acid, pKa 7.5. I've been noting all this stuff down. So we'll actually pretend like we're in the real exam at this point, and we'll make some notes. So first of all, we can see we've got HOCl. Well, right next to that, pKa is 7.5. And it dissociates into hypochlorite ions, which we can assume here are there. Is given by this reaction, blah, blah. So we might want to write that down on the paper as well. My handwriting's probably going to be pretty shocking, but H2O and then into H3O plus and OCl negative. Pool cleaner is most safely stored and transported as a granulated solid sodium hypochlorite, NaOCl, with a KSP of 4 by 10 to the negative 2. That is ionized in pool water according to this reaction. So we get it given in this form, we dissolve it into sodium and hypochlorite, and the hypochlorite then can react, and we end up with an equilibrium of this particular thing here when you put it in with pool water. So we've got a bunch of relative atomic masses. They don't seem to ever expect people to memorize those. I think it's handy to know the first 20 elements in the periodic table, but for now we don't really need that information. Some common formulae are also given here as well. I've seen this as a trend with ACER, so we're going to do the same thing. You don't need to memorize it. I mentioned that in my formula sheet video from the other day. So in solution of that should be in a solution, because classic me, I always put a whole bunch of typos in my writing. In a solution of hypochlorous acid at pH 9.5, which of the following, right? So what we're going to use here is we're going to use the Henderson-Hasselbalch equation, because this relates pH to pKa via the relative proportions of a conjugate acid A negative and the acid HA. So if we just write that out, let's just write it out first. pH equals pKa plus log 10 of A negative over HA. So really the A negative in this particular dissociation is the conjugate, which is the hypochlorite, and the HA is the protonated form, which is the actual acid itself, right? Now we're already told that the pKa was 7.5, and we're told the pH is 9.5. So what that means then is, if my whiteboard wants to work with me, there we go. 9.5 is equal to 7.5 plus log 10. Let's actually put our actual real expressions in. I leave out the square brackets just because I'm a bit lazy and they're a bit annoying to write. Yes, they are actually concentrations, but I'll save you the trouble there. We minus the 7.5 across, we get 2 is equal to log 10 OCl negative over HOCl, like that. And we can rearrange this. So now 10 to the power of 2 should be equal to OCl negative over HOCl. And if you've seen my logs and exponentials video, I explain the way that I rearrange logs is I just use the concept of bracket equals base to the power of the answer, where each of those 3 parts are part of the log. So here the brackets are, probably should be in brackets, this fraction is equal to the base, which is 10 to the power of the answer, which is 2. And that really means 100. So this is the ratio of these two things. And so what that actually means is if I want to multiply this over, let's put the actual square brackets in this time. it actually says mathematically that the concentration of the hypochlorite over here is 100 times the concentration of the acid. So now we can go through and we can see the only answer that says that is C. You'd probably want to go process of elimination because maybe there's some other variant way that we could express this. We could say that the HOCl is 1/100th of the concentration of the hypochlorite and reverse it. But in that case, then we know here the conjugate is 100 times more concentrated than the HOCl. Simple as that. So then question 2, if a pool treated with pool cleaner needs more pool cleaner to be added, but someone accidentally adds in a commercial size bag of table salt, the most likely outcome will be. So because there's no numbers here, this hints that it's more about proportionality or it's about direction. And in this case, that would mean that I could use Le Chatelier's principle. I'm not going to have to be subbing into formulas too heavily because I don't actually have any numbers to help me out here. So if I just go, it says there's already a pool. So we've got this mixture already happening. And then we go adding in a bunch of sodium chloride. So where can I see that? Obviously there's no actual sodium chloride here, but remember that as soon as you put sodium chloride in water, it will dissociate into sodium ions and chloride ions. Effectively, the sodium chloride, adding it in, is effectively like a source of sodium ions. So we're massively bumping up this here. What's that going to do under Le Chatelier's principle? It's going to favor the back reaction, which would consume hypochlorite. And that means we get a decrease in the hypochlorite. If we then link that over to here, that's coming from the pool. So we also in this one have linked a decrease in hypochlorite as a result. And you can see all the answers are related to pH mostly. So I'm trying to get to this here, the hydronium. And so if we have a decrease in the hypochlorite, then in this case, this will actually favor the forward reaction. And that will lead to a production of hydronium along with a production of hypochlorite to try and balance it out. But the more important thing is this here. So if we have an increase now in this as a result of all of these responses, then we have an increase in H+, which means we have a decrease in the pH of the solution. And so that would lead to a decrease in the pH of the pool water. So we know that B is the complete opposite, so that's already out just on that. C says a decrease in the density of the pool water. Technically, we don't have a lot of information about density, but we do know that there is a conservation of mass. So even if you're adding a chemical and it's changing its form or it's changing its identity, the mass of all of the stuff in the pool is the same. You've added solid, which means you haven't changed the volume. So if we think about what density is, it's mass over volume. We've basically kept volume the same, but increased the mass by adding more stuff to it. That would actually increase the density of the pool water, not decrease it. And obviously neither A, B, or C, we've ruled in A, so it can't be D. Question 3, this one's quite difficult. It's a little bit more heavy on the stoichiometry, so bear with me on this one. But what mass of pool cleaner would be required to bring the pH of a 20,000 litre pool filled with pure water to a pH of 6.5? So what I would do here is I would go, right, what are my kind of clues or my anchors in the question? I've been told about the pH of 6.5. I'm trying to work out a mass of pool cleaner. And remember, pool cleaner is just a fancy way to say sodium hypochlorite, like that. So here is where I'm trying to work out. I'm trying to get to that point. I've been told about pH, which links over here. I'm going to try and stepping stone my way towards it. So the first thing is if I have a pH of 6.5, then the pH, remember, was equal to pKa plus, and then the log 10 of the hypochlorite over the concentration of the acid, like that. So I do have a couple of numbers here. So I know that the pKa is 7.5. I know the pH is 6.5. So I can actually start solving just like we did in the first question. HOCl. So I can minus the 7.5 and then get -1 is equal to log 10 of OCl negative over HOCl. And therefore 10 to the -1. Make sure that's a little bit neater. I might zoom this in a little bit. That is going to be equal to the ratio of OCl negative to HOCl, like that. And so if it's a saturated solution, what that then means is that, so the KSP of the sodium hypochlorite like this, we need to dissolve it in there. that was 4 by 10 to the negative 2, was it? What was it? Yeah, that was 4 by 10 to the negative 2, like this. And remember, that would be the concentration of the sodium ions multiplied by the hypochlorite ions. And so because these two would be equal in this particular case, then we would say that we could just say that the hypochlorite times the hypochlorite is equal to 4 by 10 to the negative 2. And so then that means that we can square root effectively, because this here would be the hypochlorite squared, 4 by 10 to the negative 2. So we can solve the hypochlorite concentration at equilibrium, and that would be the square root, which would be the square root of 4, which is 2. We'd halve the power on that, and we've got our hypochlorite concentration. And that, in simpler terms, is 0.2 moles per litre. Now, what we can do over here is we can then see that the ratio is a 1 to 10 ratio. So if we multiply the HOCl this way, it means that, like, a simpler way to look at that is that the OCl to the acid is a 1 to 10 ratio, right? Because that's what 10 to the negative 1 is. So for every 1 moles per litre of OCl, we have 10 moles per litre of HOCl. So we can do that here. That means that the concentration of HOCl is actually 10 times greater, which is 2 moles per litre. And so now we know that in the whole system, if we write the two out, we had the equilibrium system into H plus and OCl negative, and we were told, or we know that this is 0.2, we know that this is 2 moles. Overall, if that's at equilibrium, we have a total of 2.2 moles per litre sitting in the solution itself of both of them. The reason why I'm adding them is because they have the same volume, right? So they're a 1-to-1 ratio. They have the same volume. So therefore, the number of moles we could add up. We don't have to actually know what the number of moles is, but because they're in the same volume, then they would be proportionate to the 2 and the 2.2. So we're almost there. So then finally, what that means is that if we've put 2.2 moles per litre worth of stuff through the pool, then what we can do is we can go, what is 2.2 moles per litre? Well, that would have been calculated as some number of moles divided by a volume, and we can work that out because this was 20,000. We can times that across. Let's write the 20,000 as 2 by 10 to the 4, and we get the number of moles is 4.4 by 10 to the 4. And then finally, we can get the mass of that thing there, because it's all 1-to-1 ratios as well. So the ratio of the hypochlorite to the sodium hypochlorite is 1-to-1, which is why we can take that shortcut. And so now the mass of sodium hypochlorite there would equal number of moles times molar mass. So that's 4.4 by 10 to the 4 multiplied by, and the molar mass here would be 23 plus 16 plus 35.5, which gives us kind of around about the 75 mark. So 4.4 by 10 to the 4 times by around about 75. And if again, we just call this 4 by 10 to the 4, and we'll call this 7, well, we'll just call it 7 even. 7, so we'll round this one down. I might actually round this one up. So we'll round that up to an 8, and that can be 8 by 10 to the 1. 4 times 8 is 32. Index laws, 4 plus 1 is going to be 5, and then we get 3.2 by 10 to the 6. And remember that standard units for mass is grams. So this is the same as 3,200 kilograms, which is also 3.2 tons, which is a gigantic number because I didn't really plan the question out, but maybe it seems about reasonable. And so the best answer then is C, just like that. Cool. Question 4, it's also known that the Henderson-Hasselbalch equation can be applied to bases, as this particular formula demonstrates. So if the pH of a pool is 6, then the pKb of a hypochlorous acid must be which of the following? So the trick to this question is that we're given information about the acidity, but then the question is really about the basicity, pKb. So what we want to do is we want to relate the other Henderson-Hasselbalch equation to this one. So that was pH equals pKa plus log 10 of A negative over HA, like that. And remember that we know that pKa is 7.5. So what we could do is we could start with 6 is equal to 7.5 plus log 10 of A negative over HA. And so we can minus the 7.5 across. and we get negative 1.5 is equal to log 10 A negative over HA. And then from there, we can go 10 to the negative 1.5 is equal to A negative over HA. So from there, what we can actually do, you can change the way that you look at it. These are just generic terms for acid and conjugate base and conjugate acid. So if we just write out HOCl and then into H plus and OCl negative, here we're talking about this is the A negative and this is the HA. When we're talking about bases though, I'll do it in another color, we could think of this as the base and this can be the HB if we're talking about the reverse reaction where it's acting as a base, the conjugate. And so really what that means is that if we want to talk about HB, this here at the moment is equal to OCl negative over HOCl. We could just reverse this and go, well, we want HOCl as a ratio of OCl negative. And that would just be the inverse of this, which just flips the power on the sign to a positive, 1.5. And we're ready to go. Now we can plug that in over to here. So when we do that, then we're going to get POH equals PKB, and then plus log 10 of 10 to the power of 1.5. Like this. We know our POH is just 14 minus the pH, which was 6. And that is equal to, that should say PKB. PKB. This here, we can bring the 1.5 down to the front and the log 10 cancels out. So you get plus 1.5. So then you've got 8 is equal to PKB plus 1.5, and you can minus the 1.5 across and you'll get 6.5. 6.5 is equal to PKB, like that. So that gives an answer that's not there because I must have made a silly mistake when I was writing this question. So it'll already be changed and A will be 6.5 and that will then be the answer. So that is a lot heavier in the maths than you should really expect. Realistically, it's not very well prompted. It's really just an absolute test of people's ability to navigate through. So those last two are particularly heavy. I wouldn't be too fussed about them if you found them difficult. The more important thing to take is just how we can derive new formulas and sub one into the other, use log laws and that kind of stuff as well. Cool. All right. Then we'll go through unit 2 now. So this one is looking at fatty acids. So I've given a table of saturated fatty acids with their formulas, the number of carbon atoms in their names. We've got saturated fatty acids are compounds that contain no double or triple bonds. Unsaturated have at least one of those. Saturated fatty acids can undergo dehydrogenation reactions, and this is generally achieved with the use of an FAD-linked reaction catalyzed by acyl CoA or coenzyme A dehydrogenase. So this here is just helping with the catalytic conversion. That is just the catalyst that's going to be used. Generally, the dehydrogenation occurs on the alpha and beta carbons of the fatty acid, which are the adjacent carbon to the carboxylic group. Here's the carboxylic, which has been attached with a coenzyme A, and there's our alpha carbon, there's our beta carbon, like that. So the wording that I've put together is extra confusing, but really the diagram helps out. This is a common trick that you can use, so you don't always have to read in too closely to the way they present things. Question 1 says, what would be the molecular formula of stearic acid if a single dehydrogenation were performed in the presence of FAD? So all of this, they do this kind of thing. They'll give you an enzyme name or something, and they know because if they put it in every question, it's going to sound really long and lengthy. That just means another way to say this reaction pathway is happening. What do we get? So in this case, what would be the molecular formula of stearic acid if it's undergone a single dehydrogenation? We can see that dehydrogenation adds a double bond and it removes a hydrogen from here and here. So we always lose 2 hydrogens for every double bond or every dehydrogenation. So in that case, if we go to stearic acid, we can find it here. It'll basically be this, but you'll just lose 2 from the 35 hydrogens. So it should be C17, H33, and then COOH. And so therefore that gives us answer D. Nice and easy one. Number 6, then how many mole of FAD would be required to produce 3 mole of this particular compound via dehydrogenation? So the only thing, this is our product. this has to have come from a compound that has the same number of carbons in it, right? Because dehydrogenation says in the stem, there's no loss of carbon or anything, there's no gain of carbon. So if it's got C15 at the start, we'll go and find that. There it is just here, and I'll get rid of some of this scribbling. So here it is, C15, like this. It started off as 31 hydrogens, right? And so if we look at what we've got now, we've got 27. So the gap between those is 4 hydrogens have been lost, and every two hydrogens is a double bond. So this means 2 carbon-carbon double bonds have been created, and each of those double bonds uses an FAD. So that is a 2-to-1 ratio, right? There is a 2-to-1 ratio. So 2 FAD to every 1 fatty acid, we'll just say like that. So if we're trying to make 3 mole of fatty acid, we would need 6 mole of FAD. And then that will be option B. So it's technically a mole ratios concept that we see in chemical equations, just put in a reaction pathway. They like to do that. So then finally, it's also known that there are different types of acyl-CoA enzyme dehydrogenases. There's the long chain LCAD, the medium MCAD, and short chain SCAD. A study was conducted into exactly what carbon chain lengths each of the variants respond to. This was achieved by measuring the melting points of each of the fatty acids before treatment with each variant of the enzyme, and then again afterwards. The results are summarized, and what I've done is I've created a code because they like these plus minus tables. A negative implies that there was no impact. A positive implies that there was a decrease in the melting point. So we know that adding double bonds in place of saturated bonds decreases melting point because these are much, much easier to interrupt and break. So what that then means is that if we have a positive sign, it means that we've added double bonds, and therefore the enzyme was allowing dehydrogenation. It was catalyzing dehydrogenation. So I won't go through the whole table here. We'll go straight to the question. Based on the above data, which of the following statements is false? So dehydrogenation of caproic acid can be catalyzed by 2 enzyme variants. So we need 2 positives against it. We go to caproic and we can see that both the medium chain and the short chain both worked on it. So that would be true because it says 2. So that's true. So therefore that is not our answer. The medium chain has a smaller range of fatty acid substrates than the long chain. So there we want a wider range of compounds that it works on. And the medium chain worked on, we've got a plus here and a plus here. And then it worked here and here. So we had 4. Versus if we look at the long chain, that one worked on 1, 2, 3, 4, 5, 6. So the medium did have a smaller range. So that is also true. And then the long chain will only work on fatty acid chains containing more than 12 carbons. So with this one, it's a bit of a pain. I'll get rid of some of this. You have to kind of go through the names and work out where the 12 carbon one was. So we find 12 carbons that linked to lauric. And if you go through the process, you'll notice that I've just basically made them increasing in carbon number as you go across and down the rows like this. So lauric was number 12. And this says long chains will only work on fatty acids containing more than 12. And there it is, more than 12 when you push above. It doesn't work on 12, but it does work on all of those above. That is also true. So we know it's D, but let's just confirm it. Long chains will require more FAD molecules than short chains. So it seems reasonable because it's like you could fit more double bonds on there and therefore you need more FAD, but we don't have enough information to prove that. So that is not a true statement completely. And so therefore that would be a false statement to make, absolutely. So the answer then is D, like that. Cool. All right, so hopefully that was helpful. Hopefully that kind of got you thinking about the way to break down some more kind of chemistry, acid-base questions at the top, and then also just a little bit of like a kind of hybrid question of organic chemistry, but also just some general chemical principles as well with some more ratios and some data analysis stuff as well. Let me know what you think of these videos. Let me know how you went with them as well. Hopefully the study's all going well and things are still smoothly sailing towards March 18th/23rd, and we'll see where we're at next week. If I can try to get another one of these in before the sitting, I will give it my best, but I know my own study is starting to fall behind a little bit, so I'm going to try and make sure that I prioritize that. So I'll let you guys know where I'm at. But otherwise, I will see you guys in the next video.